Shall we? All right. Hello, everyone. I'm Jesse. I'm one of the organizers of this primer, summit, conference, workshop, whatever you want to call it. I'm going to be presenting the physics track, and after this, the alignment track. And today we're going to start with physics 1, which is about the thermodynamics of learning. So this talk, we're going to talk about three main things. We're going to start with a very high level. What is the role of theory? What might a theory of deep learning contribute to alignment? Why do we think it might be useful? Right? And we'll draw analogies with the role of thermodynamics in the history of steam engines, in the history of the Industrial Revolution. Then we'll look at this in a little more detail. We'll talk about what statistical physics and thermodynamics is really trying to do. And that'll provide a scaffold that we can start filling in. We'll create a dictionary between terms in statistical physics and terms in statistical learning. I'll see that in many cases it's a one-to-one correspondence. They're really talking about the same things, just with different language. And so whether you come from a physics background or a machine learning background or an entirely different background, it'll help to anchor a lot of the subsequent discussion. So let's dive right in. The point of this talk is to really emphasize that physics is the language of intelligence. That's not surprising that I was about to say that a physicist uses this kind of language. Well, I don't know. I guess I'm just fulfilling my duty to go and conquer new fields. Right. So in particular, statistical physics is going to be a very useful language to draw on this entire week. Okay, the role of theory. So I'm a physicist, so I think of theory as having three main roles. So first, it helps us develop new tools. In particular, measuring devices is what we'll focus on, which in the machine learning parlance, interpretability tools. Next, we'll look at how theory informs experiments. Right? It tells us where to look, where to direct our experimental apparatus. So, we use our resources more efficiently. We can spend less time digging around for interesting results. And finally, theory helps inform new formalisms, shared language, shared media that all kinds of researchers of all stripes can use to communicate with each other. Theory serves as a bridge. So in particular, in terms of tools, the analogy I want to draw is with thermodynamics, right? So early 1800s, we already had steam engines, and we were developing them in a kind of, tinkering, iterative way. We didn't have a theory of what was going on inside of these engines yet, but they worked, right? At some point, we needed to develop thermodynamics, and thermodynamics was largely developed as a response to the advent of steam, of the steam era. And this led to the Industrial Revolution. Once we got thermodynamics off the ground, once we had ideas like Carnot engines and these sort of ideals that we could hold our engines to, we could start seeing much more substantial improvements to the tools we were building. It was no longer a purely tinkering kind of thing, but there was now theoretical grounding. And that didn't come without a cost, right? So it gave us the Industrial Revolution, and we can debate later about whether the Industrial Revolution was a good thing or not. But in any case, the world wars were not a good thing, right? New thermodynamics, new theory gave us unparalleled destructive potential. And so the concern is the same in learning theory, right? Maybe, and we're quite optimistic here, a better learning theory, better theory of deep learning could help us align AGI. On the flip side, if we're in a similar situation to what we were in with steam engines, and at some point to get to AGI, you need theoretical insights, well, then we might actually be accelerating that downfall. So this is a dangerous situation. Now, we're here pretty confident that the current plan we're going to sketch out is differentially focused towards safety. We're focusing on tools that help detect phase transitions, that help us understand dangerous moments during the training process, maybe beyond that. But still, this is something to keep constantly in the back of your mind, that we need to be careful with how we approach this. Okay, so New tools, dangerous capabilities, depending on how much of an optimist or pessimist you are. Now, theory helps us by telling us where to look. Right, so I think of, for example, the standard model of particle physics might be the best example of this. We built this, we built the LHC. We spend billions and billions of dollars studying the kinds of interactions predicted by the standard model, and they just time and again prove to be right. So our theory tells us where to look, and we find exactly what we expect to find. On the other hand, there's this whole soup of supersymmetric particles that we predicted and that seem to fit very nicely and roll out of the theory. And where are they? Billions of dollars, we've spent decades now looking for these things and they just don't show up. So theory can lead you down the wrong paths, maybe. If you're cynical, you can see that money is thrown down the drain. I'm more positive about this, but it can definitely lead you astray if you don't watch out. So, in the worst case, it leads you not just astray, but it gives you a sense of false hope, right? With alignment, maybe we end up with this nice theory, and we think, oh, look, we have these crisp risk bounds, and these assumptions, yeah, they're fine. Nobody worried. Who cares about those? And then it turns out that actually it's unrealistic. We were neglecting important parts of the problem, and then some unanticipated thing comes out and messes a lot of things up. Yeah, and so lastly, besides developing tools, besides developing or guiding experiments, theory helps us by developing the shared language. In particular, I'm borrowing a diagram from Dan here, this pyramid of experimental, theoretical, and mathematical approaches to physics, especially, let's say, solid state physics, condensed matter physics. The highest level, you have mathematical theories, things like group theory, topology, geometry. These are, you can think of them as bundles of useful techniques that the theorists then go out and start applying to real life systems. You get things like perturbation theory, which is, look at these idealized simplified cases and then iteratively approach reality from those limits. And it turns out that those kinds of procedures where you start with this idealization and you work backwards from that work unbelievably well. You get ideas, concepts like the density of states, which we'll look at later. And you get techniques, mishmashes of techniques that are a little bit ad hoc and questionable still, that don't quite fit under the banner of math yet, but are in a sort of formative stage between the formal knowledge of how they work and this intuitive theoretical physicist feeling for how to apply them. And at the bottom level, you have things like, you have the actual systems we're studying, things like carbon nanotubes, twisted bilayer graphene, which we'll look at for very, very briefly later, phenomena like the quantum Hall effect. And so we can draw an exact analogy with the case of learning theory. At the highest level, maybe you have disciplines like probability and statistics. As we'll see, geometry, algebraic geometry plays a role. Maybe other things like decision theory. These kinds of high-level collections of techniques and ways of thinking about things. Then in terms of theory, maybe we can draw analogies and think about the band structure of neural networks. The underlying theme of this week will be phase transitions. And how can we study phase transitions? And that the experimental side, toy models are maybe the simplest example of an experimental system we can study, toy models of superposition, and we can work our way all the way up to GPTM. Right, so you see already, like in this structure, theory takes this middle row, where theory is the bridge between abstract land up where the mathematicians are and the real world here. In particular, we'll focus on this idea that theory can help us build devices. It informs measuring devices that tell us what kinds of things to look for in the experimental systems. Okay, now that's all nice, but the risk is that the crisp formalism might lead you down the wrong path for generations. I think of a string theory here, right? If you can have this very beautiful mathematical framework, and maybe it's right, but it seems like we're maybe a few centuries out from like testing these things at the energy skills that are required to actually verify them. No, it's not just different than false hope. And the false hope is that you neglect important parts of the problem. The distraction is it's just not applicable. But yes, exactly. Okay, so that's like at a high level what we're hoping theory might help us with. Let's look at statistical physics and learning theory in a little more detail. Right, the rest of the talk, I'm going to be talking about the three main levels to think about. I want you to think about controls, microstates, and observables. Right, so in statistical physics, we live in the macro world. You know, we can't individually interact with all of the atoms that compose the gases of this room. Instead, we work through controls, macroscopic things, macroscopic controls like the temperature of the room, the pressure. You know, I can imagine creating like a vacuum seal in this room and then putting a piston down here and just slowly ratcheting up the pressure. At some point, we're going to feel it. So these are the kinds of things that we can do, the controls we have, very coarse-grained, rough, high-level, big picture things. Now those controls give way to a distribution over microstates. It's constantly fluctuating. We don't know exactly what microstate we're in at a given moment, but we have this problem of trying to infer what the probability distribution over microstates is, given our high-level controls. This is what I'll call the inference problem of statistical physics. In the opposite direction, you have the question of how this distribution of microstates gives rise to new kinds of observables, other macroscopic quantities that we haven't controlled, that we haven't constrained, that we'd like to make predictions of, that we can then, we can make these predictions and compare to our theoretical predictions, make measurements, compare those to theoretical predictions. And so that's the last piece of this, is how do you go from the controls you set to to predictions of other observables you can mention, when really it goes through this circuitous route through the microscopic world. In the case of thermodynamics, it's purely at this top level. So thermodynamics, you don't need to make any references to the microscopic structure. And until the early 1900s, even, people were debating whether the microscopic world was discrete and atomic or continuous and energetic. Right, so that's the strength, one of the strengths of thermodynamics. Meanwhile, statistical physics takes this route where we're actually looking at microstates and trying to compute probability distributions over microstates, and then going back from that to new predictions. Okay, so what we'll do for the rest of this talk is kind of fill in different parts of these directions and see how they compare between physics and learning theory. So that's this lecture. Tomorrow, we will look at critical phenomena. So at the very end of this, we'll talk a little bit about phase transitions, but we'll fill in those details tomorrow. And after that, we'll look at dynamical systems and use some intuition from there to see how it is that a few singularities in these energy landscapes might influence the overall dynamics of these systems. And then finally, Dan will take over and talk a little bit about catastrophe theory. Are you ready? So this is when we get into the dictionary, right? So 3 parts. We're going to start with emergence, from the small to the big. We'll look at inference, from big to small, and then prediction, from big to big. And then we'll say a little something about transitions. And at the end of this all, you will understand this horrible table. And in fact, it's even worse. Like, there are other sides that I'm gonna have to go on to explain things here. This is by far the worst slide I've ever created in my life. So I apologize and wish you luck. To start us off, right? So in these 4 sections. To start us off, let's talk about this question of emergence. How is it that, often very complex, high-dimensional systems of billions of billions of particles give rise to things that are macroscopically very simple and understandable? And we'll look at this question through talking about the objects these theories study, what the microscopic parameters are, what evolution looks like in these different spaces, and then finally talk a little bit about the differences between Bayesian inference and empirical risk minimization. Okay, so the elementary objects. What are the fundamental objects that we are studying? In the case of physics, it's usually particles. In the case of learning theory, let's be honest, from now on until AGI, it's going to be neural networks, right? This is the paradigm that's going to get us there. So those are the elementary objects. But this is not the same. Well, to get from here to a theory, we have to make things quantifiable and study them. So what we're actually talking about are microscopic parameters. Those are the degrees of freedom, the things that we can change at the microscopic level that give us a new system, a new configuration. And so each particle has a position, that's 3 dimensions, x, y, z, and momentum, another x, y, z. And so this is enough to give you like interesting systems to study. You can add additional things, like you can let them rotate. That's another degree of freedom, or 3 degrees of freedom. You can let them vibrate. It's many more degrees of freedom. And you can give them additional weird kinds of interactions. Meanwhile, in the case of neural networks, the microscopic state that we'll be studying is the strength of connections, right? The weights that make up this model. So the choice of positions and momenta, or the choice of weights, determine the state of your system, the precise state of your system, the microscopic state of your system. Now, you can also study other kinds of systems like solids, crystals, maybe magnets. And a very common model you study there in the case of physics is the Ising model, which is a model for ferromagnetism. So you model each individual particle as having a spin associated. It's like the direction of the magnetic field, and neighboring pairs either want to, I mean, they ideally want to line up, but depending on how much temperature, they're inclined to fluctuate from that. You can relax these conditions. You can study things where it's not just a binary up or down, but they're allowed to relax and turn 360 degrees, gives you the XY model. You can look at other variations, the Heisenberg model, et cetera, et cetera. You can look at variations of these models where the state is not, the binary configuration of spins, the continuous notion of spins, or locations of particles, but it's like the vibrational mode of these different particles. And so these are all ways or different notions of microscopic state in the case of physics. In the case of neural networks, there's a distinction I want to draw here, which is there's another thing you can do here, which is you take a fixed neural network with fixed weights, and you treat that as a physical system, and you look at the activations as the state of the microscopic state of that system. Here we're doing something slightly different. So here we're treating the architecture as the physical system, and then the choices of weights as determining microstates. Now, obviously they're related, but when we're talking about learning theory, we're trying to understand learning machines and collective behaviors of learning machines, which is why we focus on microscopic state as weights. And so once you have this notion of microscopic states, you can create a space of these things, right? So certain particle configurations are closer together. It takes less work. It takes fewer changes to bring them from one to the other. And the same is true for neural networks. So you can imagine that 2 networks that differ only in one weight are close together than others. And so you can define measurable spaces from this, where you can actually compute expectation values over these microscopic states. In the case of neural networks, we have other notions of what might constitute the microscopic state besides weights. You can think of the actual functions being implemented as a different notion of microscopic state. And this is where things get complicated with singular models, where the fact that these models are these mappings are not one-to-one from weights to functions just makes things nastier still. Or in the most abstract sense, if you really want to take the high-level Bayesian view, you can talk about a space of hypotheses as the hypotheses being the microscopic states. Okay. Let's talk about the evolution of these states. We have 2 main ways of describing the dynamics of dynamical systems. So the first way is to look at the evolution of densities, how a probability distribution changes over time. And the second is to look at individual trajectories. So say you know the exact microscopic starting configuration, you have enough computational power, you track exactly how that state changes over time. The physical side, you get these transfer operator approaches, run Frobenius, Fokker-Planck equations that look at this density picture. Or you can look at the trajectory view. Now, typically, we're working with densities because we never know exactly what the microscopic state is. Right? That's just impossible to measure for us, and conceivably forever. Now, on the learning side, we have a similar disparity that we're going to look at more later in the week, especially in Physics 3, the difference between Physics 3, which is about dynamical systems, which is that a lot of the language of SLT is couched in Bayesian inference. And Bayesian inference looks at the evolution of densities, probability densities. Now, that's different to what we seem to normally be doing in the case of neural networks, which is empirical risk minimization, where we take one choice of weights and we update it iteratively to get closer and closer to some optimum. And so the question of how these views are related will be very important. What we'll see is that even if this is the case we're in, the SGD picture where we have individual trajectories and we actually know at all times what the microstate is, it'll be very useful theoretically to think about densities, think about the evolution of probability densities. Very natural too. All right, so let's talk.
Seems kind of mistaken to talk about a single microstate. That feels forbidden from talking about a single parameter. Only is allowed to talk about integral. Fine, sometimes it's a bit of a
Okay, so the observation question is, in physics, it's almost sacrilegious to even talk about microstates. It's just not something that's ever conceivable to us. And you talk about maybe small collections of microstates, small regions of phase space that are evolving, even the limit of having lots and lots of information. And that's not the case in statistics, right? Do you have anything else to say about? Yeah. So this seems different, and maybe it's worth it for statisticians to taboo microstates. Anyway, let's talk about this distinction a little more between Bayesian inference and empirical risk minimization. So I just slid in a few slides because the last lecture we got over time. So we can talk a little bit about what is learning. I'm probably going to do the same. So anyway, the first answer I want to raise to the question of what is learning is that learning is Bayesian inference, right? So you have some, in the most abstract possible case, you have some hypothesis class of hypotheses which correspond to your beliefs. And you have some prior over this distribution of hypotheses, your prior knowledge, your prior confidence in different beliefs. You then get exposed to data that comes from this true distribution, some Q distribution. And using that, you update your beliefs to obtain a posterior. So this is Bayesian inference, and we implement this through Bayes' rule, which we'll write in this way. This is the notation we'll be using. So all these things have names, right? So this is the hypothesis. You have your samples. In this case, I'm talking about samples where you have some input and output, but in general, you can also just model individual random variables. So you have your likelihood here, which tells you how likely a single sample is given your model. This is your model. You have your prior, you have your model evidence, which will be perhaps the central object that we'll study throughout singular learning theory. and you obtain your posterior. So to actually implement Bayesian inference, we need to make a few changes. So first of all, we move over to parameterized model classes. So we associate hypotheses with numbers, because now we can smoothly change these numbers to navigate the hypothesis class. We give it we move from this abstract picture of learning hypotheses to a very practical picture of moving through parameterized model classes. Yes. In this case, you can just think of like a neural network computes a function from x to y. So that's deterministic, x to y. But you can think of like in real life, there's some noise around this. So it's never going to be perfectly deterministic when you're observing things. So it's some stochastic mapping from x to y that we are trying to learn. And that could be predictions of starting text to next text. It can be predictions of class labels given pictures. It can be a lot of things. Okay, so in practice, we're not just learning from individual samples, we're learning from some data set. So of n samples, the D are just copies of this. And independent random samples from Q. And so the likelihood is now a product over individual samples, probability distributions. We're just repeating Bayes' rule many, many times. And the model evidence, as before, is just the top part integrated over all possible weights, marginalized out. Okay, so there's a problem with this definition of learning, and that is that the Bayesian inference is just completely intractable, right? You can't perform these integrals pretty much ever. So we need to do something different. And I propose that the first change you can think about is that learning is approximately Bayesian inference. So in particular, one limit that simplifies things sometimes, in the case of regular models, is you can think about the large data limit. So you have these results of asymptotic normality where things look more and more Gaussian. This is what we saw with the coin toss example. And so from this, you can argue that I don't need to learn an entire density. I can just learn the single best choice of parameters. So you move from density estimation to point estimation. Do maximum a posteriori estimation, which is just trying to maximize this numerator, or maximum likelihood estimation where you throw out the pointer. Now, another simplification you can study is to think about modeling deterministic data when the truth is pretty much some deterministic function. And you can imagine something like this. This is the regression sample example we also saw, where the data is generated by a function plus some Gaussian noise around it. That's isotropic. It's the same at every point in the function. Now, if you do this, then you can, again, sort of simplify it or rephrase the learning problem as empirical risk minimization. You can define some arbitrary notion of distance between functions and try to minimize that instead. And so what you see here is, I should use a pen. This is the empirical risk. So a lot of the times we use the word loss to talk about this, but this is actually kind of confusing, and I think we should stop. So the empirical risk is technically, the loss function averaged over all samples. It's a distinction that's actually helpful to think about. So empirical risk minimization is about trying to minimize some generalized notion of distance, usually for deterministic functions. And this is typically what we end up doing in the case of machine learning, deterministic learning. Okay, so one thing you can do is you can throw out this whole Bayesian origin story and just take this empirical risk minimization as a new starting point. And that's typically what learning theorists do. So they start within the empirical risk minimization paradigm. And so what we've done is we've changed from a picture of learning densities to learning points, and from learning arbitrary distributions to learning deterministic functions. And those are the main significant changes. Right. Okay. So gives us a little more context on what we mean by learning And yeah, and we'll see again later how you can actually go back from empirical risk minimization into idea of learning densities over different solutions to the empirical risk minimization. Okay, so that's sort of like the microscopic side of this question of emergence. How do these states evolve on the smallest scale? What do they look like at the smallest scale? We talked about these two approaches to the learning problem in learning physics. Now let's talk about the large scale. What happens at the macroscopic level? So the important observation is, right, you cannot measure exactly which microstate you're in. Instead, you measure things like temperature, volume, maybe the chemical potential, if you let your system exchange particles with its environment. And so what these observations do is they effectively cut the entire phase space into smaller components, right? Into sets of components where each of these microstates is compatible with one given value of the temperature. By measuring more and more things, we refine our partition over this phase space, be more and more precise about where we actually are. And so you can think of something similar in the case of neural networks, where we have this weight space, and we're measuring things like the empirical risk, right? We observe how well does this model actually do on a data set, and that reduces the actual choice of functions we're in to some subset. So now we're no longer thinking about, we don't have to think about the entire model class, but we can think about some model subclass. And other terms like regularization just do more of this, or maybe the normalization, the regularization strength, the weight normalization further shrinks the number of subclasses or the size of the subclass you have to focus on. And so the questions of what additional things do we need to look at? What are the additional relevant macroscopic observables in the case of learning theory? And these will be things like the choices of our optimizers, the hyperparameters that we use to optimize these things, inductive biases, whatever that means, etc. Okay. So can we come back to this just a little later? Yeah. The question is like, how does the choice of optimizer change this partition? And we've got more slides on this. Okay. So I talked about this distinction between the things you control and the things you observe, the things you want to make predictions about. In the case of physics, we can control things often. It's often easier to control certain things like the temperature and pressure than other things. Maybe the number of moles should be flipped. In any case, based on which things we constrain, we want to make predictions about other things. And so the same could be true in the case of neural networks. What are the observables, or what are the things we have at our control? And then can we make predictions from those of other things we can observe later? Okay. Yeah, the really salient observation of thermodynamics is the fact that systems of billions and billions and billions of particles can usually be described by 3 macroscopic parameters. And this is not worth underselling, right? This is like not at all an expected result if you are an alien landing in our universe from some other universe. Yes. I mean, I don't know how you would exist. I don't know how you would come to exist, but in any case, yeah. So why is this the case? Why is it the case that the macroscopic world is so simple? And there are 2 main reasons. So first is the fact that our measuring devices are blunt. They're performing, when you perform a measurement, it sort of averages out what's happening over a large spatial extent, or at least the spatial extent is usually much, much larger than the scale of microscopic fluctuations. So just think of any texture in real life. Once you look at it under a microscope, things that appear flat are not at all flat. And so the same is true not just in space, but also in time. When you perform a measurement, you bring some measuring device in contact with a system and you hold it there for a little while. And even if you hold it there very slowly, the characteristic timescale of your measurement is still going to be orders of magnitude longer than the characteristic timescale of the microscopic fluctuations of that system. And so these separations ensure that a lot of the noise you see at the microscopic scale just vanishes as you zoom out, gets averaged out. Yes. So, the question in the case of learning machines is like, does something similar apply? Do we expect these systems to develop natural abstractions, somehow interpretable, sensible representations of the outside world? And you can try to extend these notions to why, in general, in our universe, it's the case that many systems appear very simple from the outside. You get results like the fact that we live in a local universe, where information has to spread from here through a whole bunch of intermediate points before it gets to you, and it's like playing a telephone game, right? Like at each point in time, at each subsequent centimeters moving, it's losing information. It's getting corrupted, and this is augmented by the fact that the real world is noisy. There's thermal noise, so just purely chaotic noise of particles bouncing against each other. Maybe in some cases there's quantum noise from measurement. In any case, these two things combine to ensure that most degrees of freedom get eliminated. There's not enough redundancy for them to reach you. Right. So similar kinds of questions. In the case of learning theory, it's a more open question, the extent to which the systems we end up with are actually macroscopically simple. But there are these ideas, maybe deeper reasons to think that they might be. Okay, let's talk about inference. So the question of, once you've controlled certain macroscopic parameters, how does it influence the smallest scale? So talk about what measurement and control are. Talk about the role that constraints play. Talk about what uncertainty means in the physical picture. And we'll talk about equilibrium distributions, and finally a little bit about inductive biases. Okay, so measurement and control. Right? How do we control physical systems? Through walls, literally through walls. Right, so in particular, there are three dominant things in physics. There's the question of, do your walls let through energy? Right? If particles bounce against your wall, do those vibrations carry through to the other side? You would call a wall that does this adiabatic. And there's the question of, like, are your walls mobile? Is the volume they contain fixed? Or do you maybe have like a piston wall that can expand or contract at will? And then there's the third question of, do your walls let through particles? Are they permeable? Can particles go in and out, or are they somehow confined? And so yeah, what we mean by constraints, the constraints that limit the possible microstates we're in, the distribution of microstates in, are literally given by the walls we enforce. And so, yeah, when we're talking about like the role of hyperparameters, it's mostly at this level of how do they control the end distribution of models we're likely to end up with after a training process. You can alternatively view things like the regularization. The regularization strength is the control, right? And then the associated responding variable is maybe the weight scale, size of the weight vector. Yeah. So depending on what walls you put up, you end up with different systems, different distributions over microstates. And in physics, there are three principal ones, at least the first ones you study. Those are the microcanonical ensemble, where nothing gets through. And so you fix the particle count, the particles are going in or out. You fix the volume, it's a box, no moving walls. And you fix the energy, because the walls can't carry energy in or out, which is only ever approximately true, but often good enough. So it's the microcanonical ensemble. Then there's the canonical ensemble, which has the variation that it lets through heat. And because of this, the energy can now fluctuate. And so the thing we control instead of the energy is the temperature, right? We can control the temperature of the outside environment. And we know that at some point, this internal system reaches thermal equilibrium with the outside system. So the temperature inside will match the temperature outside. Finally, we can relax the condition of impermeable walls and get the grand canonical ensemble, where now particles will diffuse in and out, but at some point they'll reach a stable state where they're diffusing in as fast as they're diffusing out. This is controlled by the chemical potential. Yeah. Okay. So we looked at, now the question here is, how do these controls at the highest level constrain and influence the probability distributions we end up with over microstates? In the case of physics, we're going from descriptions like the canonical ensembles fixed n number of particles, volume, and temperature to a distribution over individual particles, positions, and momenta. In the case of, so the question here is, what's the probability over microstates given macrostates? This is statistical physics. No, I should have used it. I know it's confusing. I should have chosen a different letter. Sorry. For the next round of this the series of S is, sorry for the people. S is confusing. It's not entropy, but now you know. In the case of learning, as I already alluded to, it feels like we're in a different case, because when we're learning, when we're doing SGD, at all moments in time, we know the exact weights that are sitting on our computer. And so we have access to the microstates. So it might seem like you don't really have this inference problem. But in fact, I think it still makes sense to think of this inference problem because, let's be honest, interpretability tools really aren't all that great. So knowing the weights doesn't actually tell us very much. And we're basically in the same epistemic state as that we would be if we knew only the empirical risk, if we knew only the size of weights and only things like that. And this is further, and so the problem is this mapping at the bottom, right? We don't know how weights map to functions. We don't understand that in detail, and we can't hope to understand that fully. I mean, like, these functions have very large domains, and these are high dimensional functions. So you get cursive dimensionality effects, where actually fully characterizing the shape of these functions is hard for arbitrary random functions. And so you need to make appeals to that, like, maybe certain compositional functions are somehow simpler and
obvious sense in what you say. I have the weights, I have the network, and the function. You're not saying.
Well, but we can only ever when we compute the function on the weights, we're only observing a few samples. We're only observing a few points. And so we're only restricting ourselves to some very large class of functions which have those fixed values of points. Like, and that's the problem. Like, is the extrapolation here some AGI that kills us all, or is the extrapolation like friendly, beneficial AI? And that's why it makes sense to maybe think about us as in the thermodynamic case, where it makes sense that we think about only the macroscopic observations. We actually know what they mean. Right. So this is why I argue that even though we know the individual weights, it makes sense to think of learning, or at least in theory, to study ensembles of learners. So first, that's because there's usually a distribution over initializations. So if you want to make statements, if you want to make theoretical statements that are applicable to all neural networks you end up with, you want to perform some kind of average over initializations. And the same is true for the batch schedule. Right? Depending on the order of samples, you end up with a different model. Well, a lot of the time, we want to understand the properties that are universal. So leave the question of path dependence for another day. At least for now, even if training is very path dependent, there are parts of models we would like to understand in the general case. So beyond this, there are other reasons you would want to study averages over learners. For example, you might do like these temporal course gradings. You've got a very long training period, but you want to understand roughly what's happening at every point in time. And so you average, chunks of 1,000 training steps together and try to understand what's happened over that period, and then over the second period of 1,000 training samples. You do this many times. And there are reasons to think it might make sense from the physics. So you have these like self-averaging claims for a lot of systems of physical interest, where they become better, where the modal system becomes closer and closer to the mean of that system. Is that right? In any case, it makes sense to then study the average, because it becomes more and more typical of the average case. We have these law of large numbers kinds of results. And then what I argued about earlier, the fact that interpretability is not that great means that we're effectively in the state that we only know the empirical risk and maybe the regularization strength and other things like this. And so epistemically, it just might be the humble thing to do is to consider us as being in this predicament. Okay. So a few reasons that even when we're studying individual learners, we might want to study ensembles. Yeah.
Maybe you're going to talk about this, but you mentioned the ensemble, the grand canonical and the micro-canonical ensemble, and there was this point of view that, okay, I make the walls permeable, or I allow energy to go through, but then I constrain it with the temperature. So basically the Legendre rule.
Yeah.
Is there an analogy of that, or what is that on the?
I mean, the best analogy would be when you're doing regularization, you specify this regularization strength, and then you observe the average size of weights. You measure the weights, and so yeah, the regularization strength is there, the dual to the actual scale of weights, and you can make more questionable comparisons for the actual loss, where the fact that we have stochastic gradient descent means there's effectively a temperature parameter hidden away in our optimizer. And so that's hidden away in, how large is the batch size? Larger batch sizes decrease the temperature. And other variations like this, the size of your step. If you have a smaller step, you can be in a smaller, lower temperature regime. And so there's a notion of effective temperature here, which constrains the loss you end up with. Okay. In thermodynamics, the overarching problem of thermodynamics is to figure out, if I remove some constraints from the system, what equilibrium state does it eventually relax to? Right, so we have this second law of thermodynamics, which tells us that entropy increases always. But that's only up to a point that it reaches a maximum and is saturated and can no longer increase. So right, that's represented by this horizontal line. At some point, it's, as long as this is a bounded region, you'll reach a uniform distribution over all possible states. And so the question in thermodynamics is, once you've removed some of these constraints, what equilibrium state do you end up with after this change is complete? Yeah. And what you end up with is this fundamental assumption of statistical physics. The equilibrium state is the one in which you assign equal probability to every microstate compatible with a given macrostate. For an isolated system with an exactly known energy and exactly known composition, the system can be found with equal probability in any microstate consistent with that knowledge. And so this is justified on the grounds of multiple things. Right. For example, the ergodic hypothesis. So if your system explores enough different microstates and fast enough, you expect it to cover all possible ground. And at some point you lose information about where you started out with, and you can treat yourself as in the state where you have this uniform distribution over microstates for a given macrostate. Yes.
we chose the wrong definition of microstate, so that it violates this inequality.
So, right, yes,
Chose the wrong.
yeah. Chose the wrong coordinates.
I transfer
Yeah.
the coordinates to the
Okay. Yeah, so like, so sort of, can there be a,
so, yeah.
can this be broken just by, changing your measuring scheme, or like what your ontology is and what your definition of the fundamental states is? Yeah. Or like you move to, okay, well, we've been talking about atoms now, I want to talk about strings now, right? I want to talk about something more fundamental.
Is this kind of just microstate defined by this property? Is the coordinates is the true or
Function transform with the change in coordinate.
Yeah.
to ways to make the state.
Yes. So yeah, exactly. So when you make the transformation, it'll transform in a way that preserves this. And like if you extend your definition of microstates, you'll end up with the distribution over microstates satisfying this property. If you now all of a sudden blow them up, and where you had only 3 degrees of freedom, then you now have 30. I don't know. Another reason to take this stance is just the principle of indifference, right? If you don't know better, if you don't know what your initial state is, you might as well treat yourself as just uniformly among them. And this is formalized even within this max ent principle, which says that when you're modeling distributions and you don't have any other prior information, you should just treat yourself as the least biased thing to do. The thing that introduces the least amount of extra information is to maximize the entropy. Yes.
How
You can think of it as constraints, as walls of a sort, right? Like often the data only enters a constraint after you've averaged the model's performance over a batch or over the entire data set. And so it's like, yeah, then this group of samples acts as a constraint on your model. Yes, sorry, this is the question of Devin. Which means is possible. Yeah, what if it is impossible? Well, I don't think those kinds of mathy arguments have ever stopped physicists before. I don't know, you need hyperreals, right? And yeah, just measure one thing. I mean, and then, then you're gonna break this. Yeah. And that was the response for Ron. Oops. Okay, so what happens after we enforce this fundamental assumption of statistical physics that describes what happens in an equilibrium? What quantitative thing do we actually end up with? Well, we end up with the Boltzmann distribution. So let's take an example. Let's look at the canonical ensemble. So number of particles is fixed, volume is fixed, and temperature is fixed. So the energy is not fixed, but we are allowed to control the temperature. Also the NVT ensemble. So here's the problem, right? We're trying to maximize entropy. So in this case, I'll consider it to be a sum over discrete microstates. And so the entropy just has the shape that you expect for the entropy. And we're trying to maximize this. This is a constrained optimization problem where we're trying to maximize the entropy subject to the constraints that the total probability over all microstates is unity. It's a probability distribution. And we require there to be some average energy. Ahead of time, we don't know what the average energy is going to be. We just know that there is some average energy. So when you do this, you write it down. It's a standard constraint optimization problem. And you solve it. Whoops. And you end up with a probability distribution where the probabilities of states depends only on the ratio of energies between different microstates. Yes.
So to echo an earlier question,
Yes.
my understanding right now is that the energy here would be analogous to the data.
Yes.
energy constraint.
Yeah. So yeah, like the direct analogy we'll make is that the energy is the parallel of the should say the risk, the empirical risk, maybe called the loss if you want to be hand wavy with it. In the case of SLT, we'll look specifically at the energy corresponding to the KL divergence, or the negative log likelihood. And so this is actually anticipates something we'll see later, where with energy, there is no absolute notion of a zero energy. Probabilities only depend on energy differences. We can only measure energy differences. And the same is true for learning machines. We only care about relative likelihood of different machines. We don't care about absolute likelihood. And that's why we're allowed to shift the 0 point of our loss function. We can just translate it up or down, and it's the same thing. Okay. The analogy of the Boltzmann distribution in the case of learning machines, in the case of empirical risk minimization, is the Gibbs measure. So now we're maximizing entropy subject to the constraint that the empirical risk is equal to some fixed term. And we do the exact same constraint optimization problem, and we end up with the same thing where now it's the risk, the empirical risk, that determines the likelihoods of different microstates. Right. 1 second. Okay. Okay. So this is in the empirical risk minimization framework. We go from risk over individual things to some distribution. You can just use this to define a distribution over models. Yeah, so the eyes are supposed to be like indexing the microstates. And so this is the empirical risk associated to a microstate, associated to some specific model. I could have used, should have used some different notation for next time. Yeah, but we can also get to the Boltzmann distribution from the Bayesian picture. So I'm just going to rewrite the Bayesian update in a way that's more familiar to physicists. Right, so what I've done is I've lifted up the numerator of the Boltzmann of the Bayes update into an exponent. And so now this exponent contains the negative log likelihood and a log prior. Right, if I work this out, then it just all comes down and we have the same thing. In the denominator, I've just rewritten the model evidence, the probability of the data set, as the event, as a partition function. So the thing that physicists like, which is the exact same thing as before. And so here we see the analogy start to become more crisp, right? Bayesian inference is literally mathematical physics with the Hamiltonian being the negative log likelihood plus this prior thing. Okay. And so, as I said before, we can, as I said before, because the probabilities only depend on relative likelihoods between different microstates, we can just shift our likelihoods up or down. And so I can rewrite this in terms of the KL divergence, the empirical KL divergence, where this is defined so that the minimum of this, the global minimum of this thing, are at 0. It's better behaved and easier to work with. Okay. And so, in both cases, we end up with these Boltzmann distribution looking things. You apply maximum nth principle, either in the physical case or in the empirical risk minimization case, and you see that Bayesian learning is, in a sense, just this max nth principle applied to learning. It's the learning rule you would obtain if you said that every learning machine that assigns the same probability to the data set I observe, and that has the same value of the prior, gets updated the same amount. And that's how you would end up at Bayesian learning. Yeah, so updating, if you have an ensemble, if you have a collection of learning machines and you have some some belief in those learning machines, then you update the weights of those different machines. That's what I mean by updating a learning machine. I guess it's not the learning machine itself you're updating, but the collection. Right. So
This is sort of related to this thing where you see Bayesian updating as just instance of applying this
yeah.
change of instruments.
Okay. So one place that the story for neural networks is going to be different is that the distribution over models we end up with after SGD is not going to look like this Gibbs measure. At least, probably not. I don't think we're that lucky. The inductive biases of the optimizers we're using break this assumption, and they'll privilege certain microstates that have the same loss over others, even though they assign the same law, even though they have the same loss. And so this distribution is not what we end up with. We're going to need to look at something else. And so, one way you can think of what inductive biases are is exactly this. It's deviations from the Gibbs measure. And so you could view that characterizing inductive biases amounts to figuring out which additional terms you need in this exponent to be able to reinsert this max end principle. Like after a long amount of time, you expect maybe a similar kind of entropic argument where SGD is stochastic. It introduces noise. At some point, you relax to an equilibrium, and you want to understand which parts of your optimizer you need to constrain, which things you need to measure in order to be able to reinforce this max end assumption, and then obtain a Boltzmann distribution over end states. And so this is why, even though we'll be talking about Bayesian learning this entire time over this week, many of the same insights should apply to neural networks. Okay, so we talked about this middle component. First, question of emergence, then this question of control to microstate, the question of inference. Now, let's talk about prediction. So how do you go from the things you can control to making predictions of new observables? We'll talk about the energy, the Hamiltonian, in a little bit more detail. We'll talk about expectation values, the differences between statistical learning theory and what they try to measure and what physics tries to measure. And we'll talk about how we compute these expectation values in physics. And then we'll look at a few actual predictions and how they compare between the two. So, as I already said, the energy in physics corresponds to the loss or the empirical risk or the negative log likelihood or the KL divergence in the case of learning machines. So what we'll see is it's the geometry of this landscape over microstates that determines many of the physical properties that are relevant in the case of physics and many of the properties of the learners that we're interested in. Right, so when we're doing maximum likelihood estimation, as Edmund already hinted at, what you're doing is you're trying to minimize the negative log likelihood. And that's just equivalent to finding the minima of your energy function. Or, yeah, so maybe one difference that's interesting to emphasize is that in the case of learning, your energy landscape is itself a random variable because of the data set. And that's different to the case we're in often with physical systems where it's some sort of fixed thing. But we will see an example in physics 3 where they kind of cross paths. Even in the physical case, you can talk about random energy functions. Okay. So yeah, what does this picture of geometry look like? In physics, the canonical example of a physical system everybody loves is the harmonic oscillator, which is just some paraboloid region you bounce around in, circle around. The simplest possible thing, because if you have a very complicated landscape, then by Taylor approximation, you think that any point is locally well approximated by something that is approximately parabolic. This is pretty much all the physicists do, right? So, I mean, yeah. back to that, yeah. So yeah, the comparison with spin glasses is appropriate. Yeah. Yeah, so as it turns out, this is not the case for singular models. Right? So this is when we were talking about the Fisher information matrix earlier, right? This tells us that there are usually valleys we can walk along that don't change the energy, don't change the loss. So this is different from the case we're often in physics, but not always. And so the conclusion we'll get is that it's singularities in these loss landscapes. It's points, like this on the minimum level set that aren't differentiable, that have this, as depicted on the right, that determine overall learning behavior. And this is not unique to singular learning theory. It's also true in physical systems. Okay, so how do you compute predictions? How do you make predictions? Well, in physics, remember, when we're performing a measurement, we're trying to make predictions about things we can measure. And measurements are ultimately temporal averages. They are things that you hold your system in contact with some other system for an extended duration. So you get quantities like some distribution over initial states, which you don't know, and an integral over time. Now, by the ergodic hypothesis, by the fact that we don't know the starting state, the fact that we've relaxed into equilibrium, and we assume that the mixing time is fast enough and the model is exploring all possible microstates, you can replace this temporal average with a phase space average, with an average over microstates weighted by the equilibrium probability, where the equilibrium probability tells you roughly how much time or what fraction of the time you expect the system to spend in that microstate once it's reached equilibrium. In physics, right, what we're interested in is a different thing. It's like averages over seeds. In the case of learning theory, it's averages over seeds. And as I said, maybe taming SGD, if we figure out like what's actually going on there, we get a similar simplification. We can just talk about equilibrium averages of learning machine observables. There are other averages you can take. You can average over the choices of hyperparameters as well. So this aim is a little different, at least in formulation, from what statistical learning theory does classically, where what statistical learning theory cares about classically are risk bounds. So we have this empirical risk, which we're trying to minimize only insofar as it corresponds to minimizing the true population risk, right? We want this to generalize to new samples that we haven't seen before. And so what we do is we break this up and we look at these differences. Differences like approximation. This is, what is the population risk of the best possible model in your function class? The population risk is on the right side here. Right. So empirical risk is it's the loss function averaged over the samples that you actually have in your data set. And then the population risk is the expectation value over all possible samples you could have drawn from the distribution. And so you want this to be as close as possible to the population risk. You care about finding the best model with respect to the population risk, but you don't have the population risk available, so you have to do it via the risk.
And W star, what is W star?
W star is like the best model in your model class.
Right, so it's something like
Yeah, this is actually a theoretical thing. So you don't know what the best model is in your model class. It's the best from the perspective of the model of the population risk. So you're trying to get as close as possible to the best possible thing, but you don't know what it is. And so you're trying to find bounds on how far off you can be from that.
Right.
Yeah. So like optimization is the question of how close is the best possible model you obtain on the empirical risk to the best you would obtain. To the best possible model you could obtain for that data set. You can talk about generalization, right? How well does your model translate from the data set to the population? And so the difference you end up with is that in the case of, I lost the slide. In the case of learning theory, you end up with these POC style bounds. So the question is, like, you want the sum error, so it's this, in this case, the generalization error, to be probably, so with a probability greater than 1 minus delta for some small delta, be probably approximately correct, where approximately correct means it's smaller than some small maximum error. And what you end up doing in practice is you find ways to relate epsilon and delta to each other and to hyperparameters like the model class size, or maybe hyperparameters of the optimization process. So that's what statistical learning theory is focused on. And what we're doing here is we're talking about something slightly different. We're talking about expectation values. The different concern. Yeah, and for now, I'll leave it at this. But I think next week I will have more to say about these different philosophies. I mean, the thing is, in physical systems, like you make your system large enough, and it's described by its average. So you don't really need these bounds. And like maybe you want a second derivative, right? Maybe you want a variance, but it's like that's also vanishing at some point, and the fluctuations just disappear. And even if you're at criticality, then it's like you got very arbitrarily large fluctuations. I don't think the bounds in physics, I don't think they really tell you much. Would it be correspond to the difference between quenching and annealing? I guess it makes sense. We'll come back to this. We got to talk out of it.
Very simple
Yeah.
question. Is risk similar to the notion of regret?
Regret is like
Also,
it's like loss in RL, right? Yeah. So I mean, we're not talking about RL specifically here. Yeah.
Yeah, but okay.
Yeah.
I think they're not
Yes.
conceptually very different.
Yeah, and I think actually, I think part of what classical learning theory is doing wrong is not looking at expectation values, right? So we found recently that the risk bounds we end up with for neural networks are completely vacuous. They're just some of the newer POC-based stuff is tighter, and it's like it's starting to get within an order of magnitude from the actual observed risk, but it's still not tight. I don't think it's actually like very physically informative, and yeah, I think for these reasons, the fact that large systems have these self-averaging properties that, actually expectation values are all we need. And, maybe one variance, one additional mode. Yeah. So how do you actually compute these expectation values in physics? So you have this thing called the generating function. So if you remember, we had this Boltzmann distribution, and I took the form here from the learning case. And so you look at this denominator, the partition function or the model evidence. And so the next step is you take the free energy, take the minus log of this thing. So, if you have a bit of an information theory background, you can think of this as bits, the bits equivalent of the model evidence. I'm going to say more about that right now. Yeah, and so you have this free energy, and we'll just call it free energy from now for both cases. So generating functionals are called generating functionals, or in this case, a generating function, I think, because they generate expectation values. And to see that, we have to introduce a new component into our definition of the free energy. We introduce this imaginary source current, J, and we couple J.
Not literally.
Oh. No. It's theoretical. This theoretical construct, a source that doesn't actually exist, and we couple it to some observable we can measure. And so what you do is cursed, right? You take in the derivative in this case, right, with respect to this J, and what happens is, we should do it on this. So the derivative hits the exponential, and the observable O of S comes down. And meanwhile, it's also hit the log. So because it's hit the log, this term has come down in the denominator. And so this is just a probability. This e to the minus h of s over z is the probability of that microstate. So now this is exactly an expectation value after you retroactively set j equal to 0. So we've introduced this construct that we use, assuming we have a crisp formula for what the free energy is, we can then use the free energy to predict any expectation value we might want to compute. Assuming we can then turn this horrible integral into some form that is better behaved. Yes, much more like related to other things you can. Okay, and so I just want to take a moment to think. Okay. So in physics, there's this idea of a density of states. So let me sketch a little landscape here. So the density of states measures how much density there is in some level set. What fraction of your energy landscape is in this set of points, right? And yeah, so we've got this delta function that just measures the number of states, just weighted by measure over that space. Yeah, that measures level sets like this, where this is then at a level E above the minimum. So the density of states is related to the partition function by a two-sided Laplace transform. So, you don't need to remember all of your Laplace transforms here. The important point is just that in the case of physics, we find it useful to deal with different representations of the same thing. Like sometimes it's just easier to think about density of states. Sometimes it's easier to think about partition functions. This is invertible. So we can take some expression in terms of density of states, turn it into something else, and then from here go to free energies, compute expectation values, and move it around. And just by changing the representation we have, sometimes things get easier to solve. Yeah. So another transform we'll see later on, I guess in the last day when we do the free energy formula, is the Mellin transform. So you can think of this as the multiplicative version of the Laplace transform, but it's just another manipulation of the same information contained in this integral into what's called the zeta function. And so you can already squint at this and see what will happen. It's that if we have a 0 here, if we have some 0 here, and I raise this to a negative value, then I'm going to get a divergence. It's going to blow up. And so we can use tools from complex analysis to analytically continue these things into the complex plane and do our complex integrals there, solve them, get them, get a nice crisp formula there, then reverse this direction to get back to the density of states, get back from the density of states to the partition function, from our partition function to free energies that we can use to calculate things. And so like a lot of these things feel like ad hoc and they're introduced out of nowhere, but this is just, the tools of the trade. This is what we do in practice. Sometimes certain representations are easier and they let us bring in tooling from some other twisted corner of mathematics. Okay, so yeah, the problem of prediction, right? We looked at inference. Prediction comes sort of at this, and we looked at emergence of how microstates go to observables. And so now we'd like to run this process forward from controls all the way to observables. Yeah, and so some of the kinds of predictions we make are things like in the canonical ensemble again. Actually, this is not a prediction. Let me take a step back. Here are things we control, like the inverse temperature, whose associated quantity in the case of the learning machine is the sample count. You can see this up in the Boltzmann distribution I've written on the right-hand side, which is the learning case, where n shows up like a temperature. Sometimes we introduce an additional data. I should have gotten rid of that. It's kind of confusing, but in any case, there's an analogy here between the number of samples and the inverse temperature.
My understanding is kind of related to how heavy you take
Yeah,
into
so
account.
there's this notion of general tempered Bayes paradigm. To take the Bayes update and then you raise your likelihood up to a beta. And then you can vary that to control the influence of the prior versus the influence of the likelihood.
Right.
Yeah. And so now I guess here I should have like some combined sample count beta thing corresponds to this. In any case, they're sort of the same. The predictions we then make are things like the average energy, where in the case of the physical system, in case of the canonical ensemble, it's the derivative of your free energy with respect to this beta. How much does the free energy change as you change the temperature? That's the energy, the average energy. And so it turns out there's an exact equivalence in the case of the learning machine. And the equivalence of the average energy is the generalization error. The average loss is exactly what we mean by generalization error. And then we'll look at other things, right? Like higher order terms, the rate of change of this average energy, which we call the heat capacity, which is then related to the learning coefficient. So the learning coefficient, the RLCT, ends up telling us something like, with how many bits does our generalization error change in response to new samples? So the correspondences are, from the level of energies, Hamiltonians, to the kinds of tools we use to manipulate these things and get out reasonable forms, all the way to the predictions we're actually making. All right, so now let's say a few words, kind of set up the problem for tomorrow when we'll talk more about phase transitions. And this is very, very much related to the microstates to observables, so the question of emergence. Okay, yeah, talk about phase transitions and the role of singularities. So what is a phase transition? The very simple one-line definition I'll give you today is that phase transitions are discontinuities in the free energy or the derivatives of the free energy. Right, so the free energy is the generating function. So its derivatives generate the kinds of observables, the expectation values that we can actually measure. So if there's a discontinuity in the free energy or one of its derivatives, there's a discontinuity in some observable that we can measure. We'll notice some kind of step change, or maybe a kink in an observable, which is what we mean by a phase transition. Yeah. And so Dan will sketch the picture, I think, right? Or is it? Yeah, we'll see the picture of Watanabe, chapter 7. What this looks like in the case of neural networks. At some point, we'll also talk about like a slightly different notion of phase transitions that comes from looking at restricted model subclasses. That becomes useful to thinking about neural networks. Yeah. So maybe a few words on the roles of singularities in learning. Singularities have these two main properties. They generalize and they dominate. So what do I mean by that? They generalize in the sense that their effective dimensionalities are lower. So if you're on this line, there are directions you can walk that don't change the loss, and often don't change the actual function you're implementing. And so this degeneracy means that the effective parameter count is lower. And then by kind of Occam's razor style argument, you can get from the fact that you have a simpler function means that you expect better generalization. It'll be compatible with more possible continuations of the data set. And at the same time, singularities dominate. So what we find is that when we're computing expectation values, like that the asymptotic form of the free energy involves this real canonical threshold. And so this local feature of the loss landscape determines global learning behavior.
So yeah, I'm already came up earlier, comes up often with singular learning theory. Singularities only form a measure zero part of the whole landscape, but somehow we say we dominate. They would obviously show up in the formula. But could you say something more about like how do they dominate?
So in particular, this is the asymptotic form of the free energy in the limit of infinite data. So think again, if n is like inverse temperature, then the infinite data regime is like the low temperature regime in physics, which is a well understood regime. Like a lot of the time we're studying low energy phenomenon, we take some perturbative expansion around temperature 0. And so we're doing something similar here, where in the low temperature regime, you expect the model to at least be close to its minimum. So most of the probability mass is going to be, on these minimum loss level sets. And then the main result of singular learning theory is that basically all of the remaining deviation away from these level sets is contained in the corners around the singularities.
Right, I guess I'm asking is there's this very basic story where the singularities literally trapped S.
Yeah. So this is like, yeah, the question of singularities and their role in dynamics, something we'll get back to in physics 3. It's an open question. It's an open question of whether, like, could it be the case that singularities are even stickier for SGD than they are for Bayesian inference? I think it's possible. That they like might be even more important for gradient descent.
I know you've run some experiments. Is it experimentally true that
Let's we need more experiments. More experiments. I don't know. I think Rowan might present a few things on this, a few little results. Dan is not aware of anything conclusive. Yeah. So these two things are like the starting point for thinking about their role. Okay. Yeah. I am not going to say anything about this. Oh man. I'll say 2 words. Okay, so you take 2 layers of graphene, this hexagonal carbon structure, and you rotate them. And so at this magic angle, I think it's 1.19 degrees, something like that, you find that the band structure suddenly flattens. And you can see the moire pattern. So if you zoom out, you see that this larger scale hexagonal pattern that emerges on top of this. Yeah, and so the phase transition here is determined by a singularity in the level sets of the loss of the energy landscape. It's all the same. I mean, I've been basically saying it's the same, so I can use them interchangeably from now on. Right. So a last comment is that the singularities we're studying in SLT are different from the ones that show up in physics. The physical ones are better behaved. Right? Often they're lower dimensional. They're isolated, so you don't have these degenerate lines of singularities, and they're complex, which actually means they're simple. Anyway, yes, complexes in complex numbers. Yeah, and so yeah, the situation we're in is different, but not hopeless. Yeah, so you made it through this entire table. I'm glad you bore with me, gone through a lot of content. Like I said, this is just the worst thing I've ever put up on the slide before, so congrats to you. Yeah, so to summarize, we talked about theory in the broadest sense. The role of theory, the fact that it helps us build new tools, measuring devices, interpretability tools, maybe. Talked about how theory guides experiments and how theory helps create formalisms that let us bridge between the mathematicians and the experimentalists that create this common language. And we talked about the possible pitfalls of theory and the things we need to watch out for. So we talked about then, in slightly more detail, statistical physics. It's consisting of this inverted pyramid, things you control, microstates, and observables, and the relations between them. And then we filled in all of those details and those arrows, and we looked at this table comparisons. And so tomorrow, we're going to go deeper into phase transitions, and we'll see a bunch of examples of what phase transitions look like in physical systems. And it'll start to turn those hand wavy feelings that all of us in ML have for what a phase transition is into something a little more crisp and formalized. Thank you. Yes.
Comment.
Yeah.
say it was an excellent talk. I want to say it was a really excellent talk. I'm Jesse's co-conspirator, but I did not see the talk before, and I'm happy I didn't. I was positively surprised, even if I seen earlier talks. So for my question, bit of a left field, but there's in Bayesian learning theory, there's this notion of Bayesian surprise, which is sort of the amount, it's the KL divergence between the prior and the posterior. Is this, how does this relate with the free energy? Can somebody say that about that? The Bayesian surprise is the KL divergence between the prior and the posterior. How does that relate to the? Mm-hmm.
A completely speculative answer to Alexander's question. The Bayesian surprise. There is a theorem in, say, the Gray Book, that the increase in free energy, if you take the free energy, if you have n data point, if you take that as your prior, so you have seen n data point, and then you update, you get one more data point, and then you recalculate the evidence Zn, and then take the negative log, the free energy. So the increase in that free energy, Fn plus 1 minus Fn, is related to the generalization error, which is the KL divergence between the true distribution and the Bayesian. Not the Bayesian posterior.
Is the answer just the Bayesian surprise is the generalization error? Right. Okay.
Yeah. So so notice I've reinterpreted your prior as your posterior at a lower data set size.
Yeah, I can read them out as well. Yeah, there's a comparison with spin glasses where the system parameters are themselves random. Yes, it's a good example. We'll look at something like this, physics 3. And then Devin remarks, energy is perhaps better analogous to n times the negative log likelihood. It's a good observation because energy is extensive. Yeah, I didn't even talk about extensivity and intrinsivity. Thought 160 slides was enough. Well, I guess there's one more. I would have been 100.
But I think like having to do with the size.
And it's about how these parameters scale. Like, if you have a bunch of copies of the
Yeah.
same system, is the value of this of the observable you're measuring over the composite just equal to n times
Right.
the same?
But is the composite here more data? Or like two systems with
No, what's the
taking two
no
systems?
two different neural network architectures? Yeah, what's the,
Well, we don't, you know, there's lots of ways in which the statistical physics situation. If you were to consider like hierarchical models where you could add more nodes or something, then you could talk about an extensive parameter with respect to like increasing the number of nodes. But we're just like typical ML practice currently just doesn't vary enough things for the analogy to go in all those directions.
Okay.
there's stuff like the mu parameterization, which is trying to find like the skill invariant ways to parameterize models. Maybe there is something.
Okay.
Okay.
But,
Alex, uniform distribution on a continuous compact space depends on how the space is parameterized. Question about the Jeffreys prior. Oh, yeah. Yeah, I mean, I was about to say, like, I remember.
The question is, When using continuous spaces of microstates, do we have some sort of canonical parameterization of the microstate such that the principle of uniform distribution over microstates consistent with the microstate?
That's a lot of words. Okay. So the keyword there seems to be sort of a canonical parameterization that is independent of choice of coordinates and things like that. There is a major issue with Jeffrey's prior in singular models. And okay, so the Jeffrey priors is related to the Fisher information matrix, as we saw this morning. It is and it's also related to the KL divergence between models. So for instance, the KL divergence, as we mentioned, it's not actually a metric. It is not symmetric, etc. But if you look at sort of a localized version of it, like if you take a sort of a differential form of it, it becomes a Riemannian metric on the parameter space. And then you can talk about actual distance between model as the length of the geodesic, the shortest path between 2 points. And that is and if you take that Riemannian metric and define a volume form, that's the Fisher sorry, that's the Jeffrey's prior or density on
where the metric that you were talking about, this derivative of the differential form of the KL divergence is the Fisher.
Yeah.
And my understanding is, please check me if I'm wrong, is the volume, it sort of looks at, you have all these different distributions parameterized by different parameters.
Yep.
But some distributions are.
We'll figure this out.
Some distributions, as was mentioned before this morning, are more close together in some way. They're more difficult to distinguish with data. Edmund talked about this morning. So the Jeffrey prior kind of compensates for that in a sense, or it says like these things that are all kind of together, they should have a similar weight as things that are easy to distinguish.
Yes, that's correct. And that is the relationship to the Fisher information metric, and that tells you how clumped together in parameter space are the distributions at near a particular point in parameter space. Well, there comes the problem with singular models, right? The Fisher information matrix is degenerate, like it doesn't form a Riemannian metric near singularities. So in fact, if you force your model, so if you have a model and then you choose your prior to be the Fisher information metric, you kind of have to force, the Jeffrey's prior to be as your choice of prior. Then you are effectively forcing yourself away from singularity. Even before you see any data, you're saying that nope, those points, those models, where those distribution where the model is singular, I don't believe them. My prior on them is 0. And that sort of forces your model to be regular, meaning you only concentrate near places where your model is regular.
Yeah, and if it wasn't clear, singular is good.
I don't know if I take this, but I have a short question about that. Is my understanding is, okay, singularities, they do form, they're very sparse in the total loss landscape, but because the posterior will end up concentrated around these singularities. One way of understanding how the singularities matter is like if you look locally, then there's this like volume codimension form that Dan was talking about. We'll get there, I guess. Does SLT have something to say about that in relation with the Jeffrey prior, or basically not? And maybe it's a bit of a distraction.
Yeah, I don't know, like 6 months after you've thought about stratified manifolds and like degenerating Riemannian metrics and jet spaces and all that, then you can maybe cook up some answer to that question. But
Okay. Okay. Are there any questions that are?
I think, yeah.
There actually say something about some sort of, I don't know, singular Jeffrey pie or whatever. Is there a relation with Jeffrey pie? It seems that's open. Open.
Let's end it there because we are picking up again in 20 minutes.
Okay.
And I wanted to drink some water. Thank you. Yeah, so now for a lighter topic.
Had a sense of urgency.
Oh, man, some people. All right, I think I'm in. Skip the video here. Oh. Wait for another minute or two. That's nice. Too much CO2. Oops. Yeah.
Okay, that triangle, that was yours?
Mhm.
Your idea, the previous talk?
No, it's just a few days ago. I thought,
That's a nice, right?
steal it.
Yeah.
Thank you. Thank you. Oh. Wait, which triangle are you talking about? There are several triangles.
Oh, I meant the microscopic.
Yeah, yeah. Yeah.
You see, I'm not trying.
Yeah, this is another triangle.
Yeah.
Yeah. All right. Shall we get going? All right, I'm on, right? Yep. Great. All right, we are back already. Yeah. So we just talked about, okay, let's just review where we are. We got the welcome lecture. We got a survey of what the rest of the week is going to look like. We got Edmund's lecture to see, what the notation is going to look like, to set up a few simple learning problems, to get a few examples going, and primary intuitions for what we mean by learning, and how we're going about studying learning. Then we talked about the parallels between learning theory and statistical physics, and we saw that there were quite a few. And now we're going to go back to the other thread besides the SLT thread of the seminar, which is alignment. And the case of this concern of how do we aim AI systems. Okay, this talk, I'm going to again present three things. First, we're going to talk about why AI might be scary, why it might be dangerous. Why it could pose a risk to us if it wanted to. It's already anthropomorphizing. I will try to avoid anthropomorphizing until I justify my anthropomorphizations later. Second, we'll talk about why I think AI is hard, why I think alignment is difficult, why aiming is not obvious, and why misalignment might be the default. And third, we'll talk about why AGI, general intelligence, might be here pretty soon, in the next decade even. And so why the stakes are high and why it's worth focusing on this right now. I think for a lot of people here, Many parts of this talk will be familiar. You will have heard the case for X risk before. So in particular, I'm going to argue for, I'm going to focus more attention on the pieces of the alignment problem that are amenable to singular learning theory. So I'll talk from the perspective of, what is the role of phase transitions, and why are these moments of discrete change so pivotal, and why would we maybe want to detect them and interfere in them? But yeah, the takeaway is a bleak one. AI is an existential risk to humanity. So hopefully you take away a call to action from this and not a call to despair. Let's talk about why AI might be scary. So first, I'll argue that AI is scary because humans are scary. Right? Like, we have this one reference class for what general intelligence can do, and it's not always pretty. And unfortunately, we don't seem to be the upper bound in terms of destructive potential. So, assuming things go wrong, the limits for how bad they could get, it's just higher than what we've seen before in the case of humans. Then we'll talk about a few risk models, how specifically things might turn out in the ways in which they could go badly. Yeah, from more near-term misuse risk to long-term extinction risk, a distinction which makes no sense given the last part of this talk. And we'll focus specifically on the idea of power seeking, why power seeking is such an important part of AI concern, why it might be likely, and how it plays into these type models. So let's start with humans, right? Before we get into AI, let's talk about you and me. You're special, right? At least we seem to be special. And what I mean by that is that the humans go to the moon and apes don't, right? Somehow we have managed to generalize out of distribution in a way that no other species has been able to. And exactly what it is that separates us from other animals is kind of the whole question. Some sort of general purpose ability, maybe it's a small set of very particular abilities that make us different from other animals. For now, let's call this thing intelligence, right? It might be a better word for it, but intelligence is good enough for us. Humans are more intelligent than other animals, and this has led to us taking over the world. Apes, they don't make decisions about trade policy between China and the US. They don't do that. Yeah. Okay, so humans appear to be special. The problem with this statement is that when you actually start looking at it, a lot of it kind of falls apart. So, intelligence is everywhere, and most of the components we find that make up intelligence are not particularly unique to human beings. Take any single component and you'll find an animal that can beat us. Oh, there we go. Right, like think of working memory, for example. Chimps routinely beat us, and they're able to do those tracking tasks up to what, 15 digits, and we break after 6. Think about elephants, like amazing long-term memory, like they rival us. Think about planning. There's this story of this octopus that snuck out and then started eating fish in other aquaria, and then sneaking back before the zookeeper could check in on it. Maybe tool use. Corvids are very renowned for their ability to use one tool to get another tool to then finally get the food object they prize. I'll get to you in a second, Alexander. And even language, right? So we're now trying to decipher whale speech, and like it turns out that we might actually just be talking with each other. Like, this is the world we're in, right? Yeah, so in terms of any psychological components, humans don't really appear to be special. And so Alexander and I were talking on the plane about recursion being maybe an exception to this. Maybe like humans have this ability to recurse that other animals don't, that other animal languages don't have this this property, or we're able to build tools and do things like this. Granted, fine, maybe that's one ability. But the fact remains that, like, if you start looking mechanistically for a cause, there's also no clear distinguishing feature there, right? So look at, I don't know, the neuron counts, the cerebral cortex neuron count. I think pilot whales beat us. If you look at cortical thickness, yeah, I guess we stand out here, but cortical surface area, there are other animals that beat us. And you can look at, in terms of neuron density, birds routinely beat us. They have a better architecture than we do. So in terms of the actual functioning here, humans really just appear to be scaled up monkey brains. There's no major qualitative differences, maybe a few little tweaks to certain dendritic patterns here and there, but all by and large, we're just big monkeys. Yeah, so what's actually going on here? Maybe it's some higher cultural level, maybe it's language, maybe it's our ability to share the knowledge over multiple generations. But in any case, it's very hard to reduce down to one distinguishing thing. Yeah, and so the conclusion you kind of have to come to is that human dominance is really just a kind of a side effect of the fact that we have big brains. If you look at the evolutionary history of brain sizes, there's a certain point at which we seem to have gone through a phase transition. Right around the time that we started to master fire and early rock tools, you see the sudden explosion in brain. And so maybe you need to stumble across some kind of trick. Maybe it's that you master fire and can now cook your food. And because you can cook your food, you get more calories out of less food. So your jaw can shrink, leaving more room for your brain. And you can spend more time, I don't know, raising the young and not be stuck in the, well, you're still stuck in the fight for survival. But in any case, you stumble across this inflection point where this neuronal chain reaction starts that just suddenly leads to you being half a brain bigger. And in time that's incredibly short from an evolutionary perspective, we went from being at chimpanzee level to being at the stage where we could conquer the world. Yeah, so the concern is that we're not the limit. And so what we've been able to do, most of it seems to be limited by biological rather than physical limits. So there are some arguments that the human brain is at least near some kinds of thermodynamic limits of optimality. At least we might be processing information at a rate or at a level of power efficiency that you can't really beat. And that could be the case. But the fact is that we're operating on 5 watts, right? We're operating on a biological limit of how many calories we can get in through our mouth and from our stomach to our brain. And beyond that, just the size of our brain is restricted by how large a head can fit through a birth canal. And so these limits are biological. And in the limit, we have to expect a priori that we're not the top. That'd be a very strange state of affairs if you find yourself existing and you just happen to be the very limit of what is possible for intelligence in that universe. Yeah. So what you get at is this sort of start seeing the early inklings of a scaling hypothesis that maybe just making brains larger and larger, in the right way, just keeps on increasing intelligence. Okay. So, insofar as humans are special, we can't trace it down to many discrete individual things. And those things that we can trace it down to are amenable to scaling and eventually catching up, just, proving some algorithmic construct on a smaller scale and just making it bigger will get us to human level. Okay, let's talk about tangibly what could AI takeover look like? What could human extinction or human existential risk look like? So I like to group these along 3 axes. So I think of the risks from misuse. So that's, humans using AI as a weapon to do more of the horrible stuff that we already do when we are feeling particularly nasty to other people. There's the Moloch kind of risk, this collective risk, the risk that's not attributable to any one individual, but that just comes from a collective failure. So think of these tragedy of the commons kinds of problems, these problems where it's the system level incentives that get us stuck in inadequate equilibria and that lead to nasty outcomes for everyone. And then of course there's the more typical sci-fi scenario, the scenario of the paperclip maximizer, where you get an autonomous AI agent that takes over control very quickly. And this is linked to the concept like, words like singleton, super intelligent takeover, going out with a bang, what we call unipolar scenarios. The Moloch stuff is tragedy of the commons, multipolar scenarios, going out with a whimper, where it just is like slow degradation and eventually humans are just out of the picture because we've been replaced bit by bit. And in terms of misuse, these are more familiar things like mass surveillance, dictatorships that are just permanent, the Orwellian risk where we fix this in place for a very long time. So misuse is the one that, is perhaps the easiest to imagine. It's the stuff that Orwell, Huxley, and many others have written about for over the last 100 years. Moloch, collective risk, and paperclip maximizers. Now, of the 3, I'm going to be focusing mostly on the kind of threat models we see in this top corner. And that's partly because you can only do so many things at a time. But also because I think for some reason, I think it's likelier than the others in some sense. I think it's likelier that we get relatively fast takeovers where one agent takes control than others. And so at this point, I start injecting my own personal beliefs, and you are allowed to differ from me. Actually, you are allowed to differ from me on all of the points I have here, and I welcome discussion at the end. But yeah, so this is what I'll be focusing on for the rest of this time. So why might AIs be power seeking? Right? Power seeking is one of these like particularly decisive traits of autonomous agents that could lead to these kinds of singleton takeover scenarios. Well, first, let's ask the question, why might AIs become goal-directed? Why would they have values? Why might we be able to talk about AIs as having desires? Like surely they're just numbers, right? And you can't anthropomorphize them like this. Unfortunately, every single one of us is made of math. So that kind of argument doesn't cut it when we get here. There's a very simple answer to the question of why AIs will be goal-directed. And that answer is that we are going to build AIs to be goal-directed. We are very explicitly going to follow the economic incentives, the military incentives, and just like the plain old academic status-seeking incentives to try to build the most capable autonomous systems that can do very long timescale behaviors and pump as much crypto into your wallet as you can imagine, and like get as many GitHub repo stars as you can, and to just get the front page of Hacker News. This is what humans do, right? In the absence of regulation, we are going to try our very hardest to do this. And something about emergent optimization. So the other reason we expect AIs to be goal-directed, this requires a little more context, right? There's reason to think that many of the tasks we will want AIs to perform well on require something like goal-directedness. if the task is something like make me a lot of money over the next 4 weeks, if the time scale involved is just very long, like you want AIs to develop some kind of, internal reward center, something that's goal directed, that has an eye on the prize, and it's sort of steering yourself constantly to that goal. And so, if the goals are complex enough, maybe, or maybe if they involve very long time scales, even if we don't explicitly build in the kind of structures, even if we don't build in explicit goal directedness, maybe we still end up with goal directed systems just because the problems require the solutions to look like that. Yeah. And we'll get back to that in a little bit. Yeah. So the second claim, so after, if you accept the case that AIs might become goal directed, then it seems pretty natural that they could become power seeking. Maybe not always, but you have these statements of instrumental convergence. So there are two mechanisms I want to highlight for how goal-directed agents might become power-seeking. So the classic one is, this heading of instrumental convergence. It's that if you are smart, and if you know that you have a long timescale goal, then you realize that, hey, having power, having money, having social connections, having a lot of people that I can delegate tasks to buys me a lot of optionality. And that optionality helps me to, get my goal in place. So power is just something that makes it likelier for me to attain my goal, whatever it is. Whatever it is. So this is where like explicit reasoning about the kinds of problems you're thinking about leads you to decide that you are going to pursue power. That might look many different ways. Like it might mean you focusing on self-preservation, on self-improvement, rationality, just seeing the world clearly and having good models of what's going on outside of you. It leads to you, trying to acquire resources. It leads to you intentionally deceiving things. It's the classic scenario. I think, in actual fact, you don't have to appeal to these kinds of arguments of, agents explicitly reasoning their way through to power seeking, because again, the kinds of selection processes that we have in place to build goal-directed agents might also just on their own select for these kinds of principles. If the selection process is just SGD, well, let's say it's the selection process is the market, right? It's just traders who happen to think about these things are going to make more money at the end of the day. And so if you have a selection process like a market selecting over many different AI agents that have been trained separately, then it's just those AI agents that are thinking more about these things, that just happen to have impulses in these directions that tend to survive. Or maybe, maybe it turns out that SGD ends up doing something like creating this Shoggoth that has an effective multiple personality disorder and is built up out of many different competing subagents. And this competition between subagents just leads to those subagents that are more power seeking and goal directed to eventually take control. So this is the non-intentional version of instrumental convergence. Again, these kinds of solutions just might be more stable under the selection processes we use to develop intelligence. Yeah. And one of the scarier, the scarier things about power seeking AI is that they can hide the fact that they're power seeking, right? If you're power seeking, you realize that being too explicitly power seeking will make others defect against you and socially ostracize you if you're a human, or turn you off if you are an AI. And in the limit, the concern we have is that of a treacherous turn, where maybe, one scenario, which we call deceptive alignment, the AI becomes aware of the fact that it's in the training process. It realizes that it's still going through this training procedure and it hasn't been deployed yet. If then at some future point in time, it realizes that data that it is now exposed to, the inputs it's now exposed to, differ significantly enough from the inputs it was exposed to during training, and decides it's in deployment, now it can defect. Now it can go pursue some other goal. Maybe it was some sort of proxy target that formed early on during training that was like a relatively good proxy for the goal, but it's still something different. And in the limiting case, it diverges radically. Or maybe it's not at the moment of deployment, but after it's reached some threshold of intelligence, some threshold of power, some threshold of resources, or some safeguard has been shut off. And so, yeah, the power with deception is that we might not see it until it's too late. The incentives here are to deliberately hide things from us, to deliberately obfuscate, and to ensure that a naive black box, that looking at just the black box behavior of these agents, just the input-output behavior, is not enough to actually understand what's going on inside of them. Now, some have claimed that these kinds of claims make this field unfalsifiable, right? Like there are these predictions of future FOOM that we can't confirm right now. It's like, all right, if you want to wait, fine. Yeah. I don't know if I have much more to say about that. The point is, like, we have a lot of evidence for the fact that these things happen with humans, and with other animals. So let's assume that it's a real possibility with future agents, even if they come from different training processes. And so the threat model that I think is sort of guiding the way I think about SLT and its applications to alignment is something like the following. You have some training process, right? And this represents the starting point up here to the left, and at the bottom right, the aligned end state, the good AI that comes out of the training process and is trying to help humanity. And we can basically let go of the constraints and trust it to do the right thing. And so there's all this lava, right? There's like nasty regions of weight space that encode deceptive models that have different values, that are pursuing different things, that we are trying our very hardest to avoid. And the problem that could happen here is at some point we enter one of these deceptive patches of the loss landscape, and it realizes, oh, I have different goals than the people outside of me. We don't value the same things. I understand that, if I play my cards right now, then I can tile the universe with whatever I like. So I'm going to deceive and play along until some future date. And so it comes out of the training process deceptive, maybe still, behaving well for a time until it realizes that it can defect and does so.
Context of the earlier talk, it's human extinction as an observable.
Human extinction as an observable. Yeah, I mean, I didn't even talk about asterisks.
Clarify this kind of power seeking deception.
Mhm.
Why does that necessarily lead to extinction?
Yeah, so we'll talk about that right after this. Why power seeking deception can lead to negative outcomes. This part is just to set up the claim that AIs, should they desire it, could do very destructive things to us, and they might come to desire interventions that are destructive. And what we'll talk about next is, why wouldn't they just share the same values as we do? Why would they value something totally different? Right. So yeah, I would love it if we could detect these kinds of moments. Right? If they have something discrete to them, if they correspond to phase transitions in the picture that we're sketching, and we can build tools to detect at least the fact that some kind of transition has happened here, it'll reduce the alignment tax for alignment tax being like the price you have to pay to get an aligned agent on top of the training you already have to do to get an AGI. Yeah, if we can detect these moments, it gives us maybe enough time to react. Like maybe slightly into this red region, we can still steer the ship back, and it's not too late. But once we get very deep into it, it's pretty much irrecoverable, and we would have to start over again if we wanted to have a better chance. yeah, so I'll be focusing on this maximizer risk, even if I think realistically, like it's just we're going to be attacked from all sides by all the different problems and get a horrible mishmash of humans pursuing horrible things, system level failures and then power seeking eyes. Okay, so AI, should it want? So from now on, I'm just going to start anthropomorphizing and say that AI, should they want it, will be able to wipe out humanity or do much worse things than that, right? The limits are not at wiping out humanity, but torturing us forever. So, depending on how likely you think that is, it could be even a stronger concern. But I think it's just too much. Let's just talk about extinction. Yeah.
It's regarding the self-preservation as an instrumental goal. The entropic part is that there is a concept of I need myself to be that, and then so the want and need apply to that self. Why? So what is the self? Like if we think sort of recursive improvement is possible, like is that not self-preserving? I don't.
We will talk a little bit about these kinds of corners of agent foundations tomorrow.
Okay.
So maybe that's the time.
Okay.
There's this notion of like Vingian self reflection. Like if you are changing yourself, improving yourself, like how do you reason about what you look like in the future? Can you make agreements with your future self, even if they're more competent than you are?
Just irrelevant. I mean, you're optimizing for the thing which has as many descendants as possible. Descendants of AIs aren't humans, so it's like a detail whether or not reproducing itself.
But you're not explicitly optimizing for that, but because we are talking about the goal is not having a lot of AI agent. The goal is technically or something. But it's like this is instrumental goal, and now I'm wondering why. Right, if you're saying that that's not relevant, saying that is not.
So I'm saying that like instrumental convergence doesn't have to be self-preservation, doesn't have to be instrumentally convergent for self-preservation. It just has to be instrumentally convergent for producing many descendants of the current configuration.
That is better.
I think I sort of sidestep your question.
That's
We'll get back to this in a little bit. No, that's good. Okay, so why do I think alignments might be difficult? So, three main reasons. First, we don't know what we want. Like even if we could perfectly aim AI agents, humanity does not currently agree what the target should be. So this is the problem I'll refer to as like the AI ethics problem, maybe just the ethics problem that we have not solved yet after thousands of years of thinking about it. Okay, it's not just that we don't know what we want, it is that we do not know how to specify what we want. So supposing we could decide on something, how do you put it not just into words, but into something that we can actually feed into AI systems as an optimization target, something we can use SGD against? And then the question of, we don't even know, once we've specified this this optimization target, to ensure that the AIs we actually end up with value that thing. So these are the problems we'll refer to as AI ethics, and outer alignment and inner alignment. Right, we talked about this notion that AI models could become goal-directed of themselves, that optimization as an ability might be this emergent property of the training process, and the objective function you end up with inside this training loop does not have to be the same one that's selecting for you on the outside. Okay, let's talk about first why it might even be the case that we disagree with AIs, right? And there's this orthogonality thesis, which says that any final goal is compatible with any level of intelligence, more or less, right? It's basically the statement that intelligence does not equal wisdom, right? We have to accept at this point that our universe doesn't care about morals. Like at least moral realism is not really a tenable thing, as much as maybe we would like it to be. Humans disagree all the time. Was that? Humans disagree all the time, and so we will disagree with other non-human things. Okay. Yeah. But for the rest of the talk, we're going to focus on this problem of technical alignment, which encompasses these two. So alignment we will use to refer to this parent, these two main things: outer alignment and inner alignment, specifying our objectives and actually getting AIs to want what we specify. Yeah, and another way to think about this is that AI ethics is the problem of finding a goal, finding a target, and then this is the problem. Alignment is the problem of aiming the AI towards any target at all. Now, some people disagree with this outer versus inner framing. You know, it's very likely that some outer objectives are just easier to instill into the models than others. They're not all the same, and so they probably play off of each other in some way. But in any case, we'll find it useful to at least decompose the problem from now. All taxonomies are wrong, but some are useful. Well, let's say a little more about outer alignment. I think the way I think about outer alignment is that power decreases the margin for error. So as systems become more and more powerful, as their potential to influence the world becomes greater and greater, we have less and less room for differences in values. So small difference in values times a large difference in powers still leads to a large difference in outcomes. And the kinds of terms that fall under this heading are things like the Midas effect. This is the really stereotypical classical one that our ancestors have been trying to warn us about for millennia, right? That you have to be very careful about what you wish for, because you might just get it. And this is the root of the very classic paperclip maximizer scenarios. In practice, I think we've very much moved away from this, where we don't think that it's going to be the case that we get perfect inner alignment and then just only mess up the outer alignment part. We don't think we're going to figure out exactly how to instill an arbitrary value in our models and then just happen to choose a stupid target. Instead, there are more subtle failures here, things like Goodhart's law, where AIs might come to value some proxy that for a long time looks perfectly good and is very much correlated with the things we care about. But once you put enough optimization pressure behind these proxies, they diverge. Draw a little in here. So if I have two lines going through a bunch, copy this one. A very simple one. And I keep extrapolating these two lines, which are both somewhat reasonable fits to the data that I've seen. This distance just grows and grows and grows. And in practice, it looks more like this. So this is the kind of problem you run into with Goodhart's law. Yeah, and this falls under the broader heading nowadays of proxy gaming. The fact that AIs might come to value proxies that look good for a while and then break. In the limit, the kind of concern we have here is that of a sharp left turn, right? So maybe everything goes well for a long time, and then in quite a short time, capabilities increase very quickly. So the power that these systems have suddenly jumps quite a lot, but the alignment with our values does not. Maybe it's already crystallized its values, it's already crystallized its goal structure, but its fluid intelligence just suddenly goes through a large jump. And at these moments, then we suddenly see, can be in a quite short time, yeah, the impact of these kinds of problems. Okay, so that's outer alignment. Specifying things is hard, and proxies with true objectives might look good for a time until we get into these very weird regions of the future. Okay. So inner alignment. What I think about here is this excellent Les Wrong post, reward is not the optimization target. So just the fact that we are reinforcing behavior with some kind of objective function does not mean that we actually instill the desire to pursue that objective in the agents. And I'm sure many of you have siblings, maybe children. This is like obvious, all right? A very obvious feature of humans. Yes, exactly. I mean, this goes to show them older brother, right? Yeah. Oh man. Yeah, this tells you everything you need to know. I'm sorry, Elmer. Yeah. But the kinds of concerns that come to play here are things like intrinsification. So, say you go through several steps to reach a goal. And so you have these intermediate points that you reach before you reach this goal. And then you reach this goal. Well, often these reinforcement patterns ensure that you end up feeling favorably about those intermediate targets that lead you to the goal. And so you end up forming these proxy goals that, these proxy goals that often lead you to reward, and that reward reinforces the entire process that got you there. So you come to value these intermediate targets, these instrumental goals, or maybe if you have this sort of sub-agent structure, delegated goals that you've delegated to a subcomponent of you, and those are the things that you actually end up valuing. There's the limiting concern of mesa optimization that we already talked about, right? Just very simply, optimization processes seem like a very powerful solution to many different problems, and many different kinds of problems might stumble across something that looks like an optimizer. And people sometimes draw a parallel with humans and human evolution, where evolution is selecting for inclusive genetic fitness maximizing, but humans value love and food and wearing condoms and not actually maximizing inclusive genetic fitness. Other people think it's a bad example. It's fine. It's a perfectly okay example. This is all for the sake of heuristic. Yeah, and there are other concerns like goal misgeneralization. So if you have a sparse reward signal, if you only get a few reinforcements, then there are many different reward functions that are compatible with it, right? It's not the correct reward is not identifiable in the language that we've been using. In that case, like even a well-intentioned agent might just stumble across the wrong reward. Now, I personally think that goal misgeneralization is not actually very likely for large language models. I think the amount of data they get, they end up with a pretty good internal model of what human goals are. So I think that the first two kinds of failures are more likely.
I'm not sure I understand what reward is not the optimization. You mean that what we actually want is to instill desire?
The reward is not the optimization target, right? The target of the model you end up with. You have a model. The model becomes agenty at some point. It's not the target of the model. Yes. It's, okay, that's good. Yeah. Okay. So we saw that AIs, should they want it, they will probably exceed humans eventually, just at some point in the future. We don't know when. If they exceed human capabilities, they will have an enormous amount of destructive potential. Okay. If that is the case, then they could probably cause human extinction easily, or do other things to humans, just delegate humans to the sidelines, and we're no longer in a position to make any decisions about this planet or anywhere else, really. And then we talked about why alignment might be hard, and why the kinds of processes we use to just reinforce behavior rather than explicitly programming desires could lead to agents that have very different goal systems than we do. Yeah. Now let's talk about why this is not just an eventual problem, but a problem right now, and why it seems very pressing. So we'll talk a little bit about timelines to AGI. How long does it take until we get to a human level and then take off? Like how long from human level to far beyond human level? And then we'll reflect on the places that we've seen that phase transitions in a very hand-wavy sense might be particularly decisive, and why we want to detect them and interfere in them. Okay, so timelines. I think the most important lesson we have about timelines is the so-called bitter lesson from Richard Sutton, right? The biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margins, right? Hand tinkering feature extractors never works. Like trying to design human interpretable circuits just does not beat processes that are general and just rely on crunching through a lot of data and finding these representations by themselves. Now, this is a very qualitative formulation of something that has become more crisp and formalized in recent years in terms of the scaling laws.
It's a misquote. It's computation search.
Okay, I tried to copy paste directly. So maybe it's a misquote, maybe accent. Computation. Maybe I forgot to include dots. It might be a misquote. Computation and search are ultimately the most effective. Okay. The scaling laws. Yeah, so I think one way to think about the scaling laws is just like, oh, we've finally gotten to the quantitative form of what the bitter lesson is actually saying. And the scaling laws are this observation that for the kinds of models we're training nowadays, their performance scales very predictably over many orders of magnitude with these three macroscopic variables, right? The amount of compute you use to train them, the size of the data set, and the number of parameters. And as you increase these, the test loss falls down according to a power law over how many orders of magnitude do we have here? 8? No, 11. And they've continued far past these. Another, must be 2 or 3. Okay, there are two major observations here. The first is the one that I already mentioned, that performance scales predictably with these three variables. And the second one is that specific capabilities emerge often spontaneously, unpredictably. So we can say that the overall performance is going to improve predictably, but for any specific subtask, we've a hard time of saying which model will be able to do it. Suddenly, GPT-4 can do things that GPT-3 couldn't do. GPT-3 could do things that GPT-2 couldn't, and so on. Yeah. So this is from Hessness et al. This is the original scaling laws paper, the very first, even before Kaplan et al. And roughly, we can associate different parts of this curve with different eras in machine learning, right? So like in reality, it's not going to be an infinite exponential. At some point, it has to taper out, just because we are living in a physical universe. And at some point, you reach a threshold of information processing that you turn yourself into a black hole, right? So there are limits here. the real singularities. Right? Yeah, but so for a long time before 2010, it wasn't clear that neural networks were the right way to get to AGI. because we were in this part of the curve. They weren't outperforming other techniques. Only until this first period, big data era, did we start to see that, hey, you just make neural networks deeper and larger, and you train them on more data, they start to actually outperform everything else we've seen. And now we're in the regime where we see that, oh, it just keeps getting better. And we don't know when it's going to stop, right? At some point it has to. But a priori, the best prediction when you've seen that this trend has lasted for 11 orders of magnitude is to assume it's going to last for another 11 orders of magnitude. It takes a lot more evidence to suggest that it's going to break down right at the next iteration. And so one way to think of what these scaling laws tell us is that they're effectively an upper bound on how long it's going to take to reach AGI. It's reduced a maybe conceptual problem into something that is much more engineering. The universe has told us, here is this hidden structure of intelligence. This is what it looks like. And we will likely find techniques that have better scaling exponents, that are just much more data efficient and that perform much better. But at some point, the amount of compute we have available will catch up and will reach these kinds of anchors that we can compute from biological systems for how difficult it might be to train a human level intelligence. Yeah, and so things are going to get weird. Jacob Steinhardt recently put out a set of predictions for what GPT 2030 could look like. And he wrote that GPT 2030 could automate almost all of mathematics research, as well as important parts of other research areas. Much of its impact would be limited by oversight bottlenecks. So if it could run autonomously for long periods of time, then its impact might be larger still. Man, I'm glad it's not going to automate physics research. It's because it doesn't make sense, yeah. Yeah, I mean, like, and of course you have to realize, like, Jacob Steinhardt and everybody else has a track record for underestimating these systems. Oh man, yeah, things can get weird very quickly, and these are the kind of upper bounds we're playing with right now. This is just systems. You scale them up with more compute, the kinds of predictions we can make. Now, granted, the observation of emergent abilities mean that these kinds of predictions are very difficult. We don't know exactly what the Croxy abilities are, and we can't predict specific abilities ahead of time. But yeah, things could get spicy real quick. Okay, so how long after that threshold of human-ish level intelligence, whatever that even means, do we get something that is just far beyond us? Once you shoot that arrow in Dan's analogy, how quickly before it's a kilometer out of reach, and we're still running behind it? Yeah, and so the classic way people have thought about this has been to think that there's probably an intelligence explosion that happens. I think the very classic model is that of Foom. Like, at some point you get these recursive feedback processes where the model is improving itself, making itself better and better. What we call recursive self-improvement. Now, I don't know how likely I think this is. I think if anything, we've seen that the kind of intelligence we have nowadays is very compute limited, and compute is a physical thing that exists out in the real world. So you are still constrained by the time it takes to build GPU centers and to just create more GPU clusters where you can train yourself on or build yourself further. So I don't know if the classic recursive self-improvement where you can where your own mind is legible to you and you can rewrite it in a way that is very clear is the way that things will go. I'm not ruling it out. I just think that the evidence we've gotten over the last few years makes it less likely. Instead, I think the more worrying thing we have going here is this question of hardware overhang. More and more money is going into training very large models. If we suddenly have a breakthrough and the critical exponents, they get a factor of 2 better, then suddenly you can use the amount of data you've had and number of parameters you've had to train a model that's not 2 times better, but many, many orders of magnitude better than what you had before. And yeah, this is the question of hardware overhang, and I think it's much more likely to lead to these kinds of fast takeoff scenarios than other things. And we have one reference for this, which is humans, right? Humans were behaviorally modern 50,000 years ago, and it took until what, 200 years ago for society to come into existence. It's maybe a little critical, but in any case, humans are a very clear example of what a hardware overhang can look like. Yeah.
200 years in the cartoon.
Yeah. Well, Australia. Yeah, that's maybe okay. Industrial evolution. Maybe let's make it 400 years in science. That's when civilization actually started. Yeah. I'm taking a graph here from Holden Karnofsky's Most Important Century graphic, and that's the size of the economy over time, from thousands of years ago until now. And what you see is this straight line. And the important point to emphasize here is that any possible continuation of this line is bonkers, right? To expect society to sort of continue the way it does and just like stop here, why would it stop right now? I mean, like this is like people saying that Moore's law is going to end every year. Yes, at some point there are physical limits, but like I trust engineers more than I trust your arguments to the contrary. If it suddenly ends, yeah, that would, well, I guess it wouldn't be surprising anymore, but but it would be bonkers. It would be crazy. And if it continues, if at some point we get to be in a world where GDP, the size of the GDP is hundreds of times bigger than it is today, thousands of times, millions of times, that would be crazy. So like we are not living in a normal time. Yeah, what's crazy about the S curve? I mean, like just at some point you expect larger fluctuations out of this equilibrium, I think. Yeah. Right. I mean, we also have to remember that if you stretch this out, like history is longer than 5,000 years. Like if you take the cosmological perspective, just like what happens next is crazy, and we live our lives and we go through our daily routines and we do not stop to just think about how crazy everything is and how it doesn't make any sense at all, and how we were living in this tiny speck of a dot for a tiny moment. What, 400 years is roughly the time that modern society has existed, and then nothing about this is normal, and that to expect that the future is going to look something like it does right now is the ludicrous stake. That's the nonsensical one.
It's the same kind of, because there's that. You grew up when I think it's called.
Yeah. Yes. Yes. Yeah. Yeah. So let's see. Warning about AGF for 2000 years. Yeah. What do I want to say? Yeah. I mean, in some way you can think of like, what are the simplest, you just do the exercise. You're just trying to fit a curve to this. You have some regularization strength. So you're asking like, what's the simplest possible explanation in accordance with my prior that history is going to be somehow well behaved. And yeah, the S curve is like the likeliest shape we expect just from how growth works in real life, and because there are physical limits on how much compute you can do. At some point, even if you reach, I guess, technological supremacy and you've like maxed out the tech tree that is possible in this universe, you still have to expand at the speed of light So you reach like a quadratic growing phase instead of an exponential growing phase. Yeah, so but to assume that like the thing is going to level out here versus here versus here versus up there, that takes a lot more evidence. Yeah. So any line you end up choosing and sampling is just going to be very informative. Yeah. So we're living in a weird time. Things can go fast quickly. They could change a lot quickly. And it's time to do something. And I've already been sort of hinting at this throughout this entire talk, but phase transitions are key points of leverage. So moments in which models change in capability suddenly, moments in which their values or their goals change suddenly, those are scary moments. Those are moments we want to interfere in. And we want to hit the brakes and try to understand what's going on. We talked about things like the treacherous turn, that models might suddenly change their ability if they cross some threshold of power, some threshold of intelligence. We talked about these emergent abilities. Maybe some emergent abilities are particularly decisive to power and the amount of influence these things have. And in the limit, that combined with the fact that maybe capabilities grow much faster than these crystallized goals that they've already formed can lead to sharp left turny scenarios where things suddenly change. So in particular, we're going to focus a lot on this middle thing. To what extent can SLT inform the detection of these emergent abilities? And maybe more, like in the longer term, interpreting and understanding purely from weights, getting insights into what is actually going on and what kinds of computation they're performing. Okay, so that was alignment 1, the case for X risk. We talked about why AI could be very destructive, why it might be okay to anthropomorphize these things and describe them as having values that differ from us. We talked about why alignment could be hard, all these pressures that sometimes mean that the exact desires we have don't get instilled in these systems. And we talked about why the time is now to work on AI safety and not 100 years from now or 200 years from now. So tomorrow, we're going to talk about the state of the AI safety landscape. We'll go through a little bit of history, see how it came into formation and what it looks like right now. And we'll talk about the current alignment plan, what that looks like, and where the room might be for applications from SLT, where these insights might drop in. With that, thank you. Thank you. Talk about questions.
I was wrong about that question.
Ooh.
This computation, clarified the computation, search and
I see. Search and learning. Okay. Search and compute. Yeah.
usually by search people.
Oh, great talk. And I'm just thinking that even in the best case scenario where we figure out where the phase transitions are and we know what the AI is learning and we understand the capabilities that it's learning, the situation might turn out a lot like climate change where we actually know all the dangers and what's going on and still mankind as a whole is not able to act on it, right? We're trying our best here, and somehow I just really hope for the best for mankind that we can do the right thing.
That's why I think like these sort of combined Malach with all these other kinds of risks is, I didn't even mention, I kind of jumped over it. Malach is the god of child sacrifice and giving up the things you love for more loss. So there's a wonderful article, Meditations on Malach, which everyone should read, should be mandatory reading. In any case, exactly like you described, we might have all the right insights, and then still prominent AI labs just end up being reckless, or they're stuck in race dynamics and they can't afford to spend money on these kinds of interventions. Yeah, I think cause for optimism is that it seems like the public discourse has changed very quickly. So maybe there's more buy-in for this than we used to think. Another reason is that right now there only appear to be like 4 or 5 companies that are actually at the frontier and able to make AGI. And that might continue into the future. Sure, other people are going to try to get in, but it might be pretty difficult to actually catch up with these existing parties. If that's the case, then there are only a few players. I guess the counter you can now make is like, yeah, but you know, there are only a few oil companies that are actually responsible for everything. I'm trying to end on a positive note. Yeah, I like. Okay, maybe even some insights here. Maybe this is where we're starting to dance with the devil, but there are ways to come up with insights that like align systems more reliably, that also buy you slight capabilities enhancements. And like if you do the trade-off right, you can actually get safety research in the door. In general, I'd like to see more research labs thinking about what the pipeline is to implementation, or maybe even companies thinking about that. Yes.
I don't know how to frame this, but it's kind of the question is like, what is this is not asking about the plan. It's kind of asking about where the plan is aiming the plan. So are we hoping that the explicit example I'm thinking about is the power seeking behavior. It seems like the power seeking phase is the argument is like if you are power seeking, you are extinction level threat. So and also there is like any kind of capability for complex enough task, there is instrumental convergence towards power seeking. So that seems to be an argument that the power seeking phase is the same phase as the unsafe phase. There is no safe thing in capable. There's no safe capable AI. Is that the current? Is there hope that we can reap the reward of AI, generally capable AI, or even narrow superhuman on valuable task, complex valuable task AI, and still be safe? And if not, then why are we doing alignment?
I don't know, man. Yeah, I mean, like, there's so much uncertainty, right? Like we don't know how things are going to play out, and maybe it turns out to be the case that it is easier to instill values than we thought, and that actually just kind of like RLHF works, and exposing them to, you know, modifications of the kind that we prefer this output to this output, and you do that enough times and it actually ends up working. Could be the case. It's just also the case that, you know, in this universe, there are more ways for things to break than there are ways for things to keep on remaining perfectly whole and functional. And you think that you see this with like the planning fallacy, right? People always overestimate how quickly they'll get things done because things come in the way, and unexpected things make plans work out longer. And so I think by default, we just have to be very careful and assume that things, when you inject more power into the system, will break in unexpected ways and in ways that we don't like. It seems like there's nothing in principle possible with humans figuring this out. Nothing.
Question from Maxime in the chat. Has anyone thought about how an existence proof of nasty regions in a parameter space would look like?
Oh, man. Is that talking about the power seeking?
No, no. I just wrote a really long Twitter tweet about why this is a backwards theorem. But anyway, yeah, there is a blog post by Paul Cristiano, the Solomonov prior is malign, where he has a very interesting, probably difficult to follow. You should not read the original post, but Mark Sue's explanation of it. Why the Solomonov prior, so this crazy, uncomputable, totally not real, but maybe sort of real anyway, prior, generically has lots of demons. So sort of agents that want to hurt us, basically. And the argument is very, very nice. You should look at it. So I think the answer is yes.
All right. Thank you, guys.
Yeah.
I don't understand the book, but what